Hi everyone, my name is Gnall and I'm a current senior studying materials science and engineering at Lehigh. This audio is meant to explain the research I'm conducting under Professor John DuPont on Monel alloys. For those who don't know, an alloy is a metal made by combining two or more metallic elements together. Monel alloys are metals primarily made of copper and nickel, but feature other elements depending on the application. Currently, Monel alloys are used in over 25 different industries because of their excellent corrosion resistance and toughness. Typically, these materials are used in the as-cast condition. However, the phases present in Monel alloys and how these phases in the material form as a result of a different type of material processing called heat treatment remain poorly understood. Heat treatment is used to improve hardness and other mechanical properties, which subsequently increases the material's life cycle. Heat treatment generates precipitates through a phase transformation process called precipitation hardening, allowing the material to be stronger. First, the material is heated at a specific temperature and time to produce a single phase present in its microstructure. This is known as solution annealing. The material is then quenched, which seals that single phase being present. From there, the material is heated to a different temperature and time to grow a precipitate that will improve material properties. This is known as artificial aging. Then the material is quenched again to seal those precipitates being present. The parameters in this process are temperature and time, which are both material-dependent variables. Niobium and silicon, two elements that are found in Monel alloys, are thought to improve mechanical properties since they promote a material-strengthening precipitate. Therefore, the goal of this research is to enhance mechanical properties through heat treatment by acquiring knowledge of the material's phase transformations, allowing us to determine what ideal combinations of niobium and silicon would best serve for better mechanical properties. Myself and the collaborators on this project initially focused on microhardness, so it was hypothesized that silicon-rich precipitates with minimal niobium will boost the material's microhardness. To achieve this goal, computational simulations using thermocalc were conducted to determine temperatures at which precipitates and a single phase would grow in 8 selected alloys. These alloys have varying niobium and silicon contents shown on the poster. From there, a procedure was developed. We decided that from the computational simulations, these samples would undergo the following heat treatment schedule. Samples first would be solution annealed at 950 degrees Celsius for 24 hours, followed by water quenching, then artificially aged at 600 degrees Celsius for varying aging times. The reason this was done is because time plays a critical role in the relationship between mechanical property enhancement and precipitation formation. Therefore, the times chosen were 0 hours, so no artificial aging at all, 1 hour, 3 hours, 7 hours, and 14 hours. After artificial aging, samples were then water quenched again. As mentioned previously, the initial focus on this work was microhardness. Therefore, samples were then microhardness tested, adhering to ASTM standard E384. Each sample received 25 indentations for each aging condition, and then plotted to generate a hardness curve. This means every point shown on the graphs in the results and discussion section is an average of 25 indentations with standard deviation. What was found is that alloys that had more silicon and less niobium had greater microhardness than its as-cast condition, where the as-cast condition is typically what we see in industry. 2 alloys compared to its as-cast condition supported this idea, showing that heat treating these materials can increase the numerical property values. Monel alloys that also have a niobium content between 1.00 weight% and 1.50 weight% have increased microhardness compared to the as-cast condition after 7 hours of artificial aging, but this happens by not a lot. This shows that less niobium and more silicon may potentially lead to a stronger Monel alloy. It was also observed that these alloys have this dip in microhardness after 7 hours of artificial aging, meaning as aging goes on, the microhardness decreases. More work needs to be done to better understand these results, but we can conclude from these observations that alloys with less than 1.50 weight% niobium peak in microhardness after 7 hours of aging, and alloys with less than 1.50 niobium and 3.0 weight% silicon exhibit improved microhardness compared to its as-cast condition. Future work needs to be done to better understand these results through scanning electron microscopy, energy dispersive spectroscopy, and X-ray diffraction. I want to take the time to acknowledge that this work could not have been done without the support from Steel Founders Society of America and Lehigh, so I'd like to take a moment to thank them, and thank you all for listening and learning a little bit more about the research that I'm conducting.